Morning, everybody.
How's it going?
It's going. Had a fun morning reading up on exoplanets, which is never a bad thing. Let me just turn off the light behind me. Otherwise, I'll look a little too holy. All right, to think of a word of the day. You know what might be useful? Rather than word of the day, let's have a fact of the day. Fact of the day. There you go. This is a fun fact to, you probably obviously already come across this. It's not, hidden knowledge or anything. This is well worth remembering. Because we're going to be talking about some really, really crazy distances. And, another fun fact as well. What's the fastest? And this is, I think it's around 0.2 C. There you go. So that's worth remembering, right? Because some of the things that we're going to be talking about are a really, really, really long way away. In fact, one that I was just looking at, which is called Earth 2.0, a little bit presumptuously perhaps, it would take us 1,400 years traveling as fast as the New Horizons probe to get there. So that's 1,400 years. What was going on around 400 BC, 400 AD? And the Roman Empire was collapsing, probably. Goths were taking over Europe. This was obviously before the Goths took over America in the 1990s. Anyway, that wasn't a particularly funny joke.
Excellent joke. I loved it. That was wonderful.
Thank you, Paul. I know you got my back when it comes to bad jokes, Paul. Although I do feel
100%. That was excellent.
I still do feel a little guilty for the whole Commiticus Chilius gag.
That broke my heart.
Anyway, tears to my eyes. All right, so I'm not sure whether people got a chance to have a look at this or not. Essentially, there's a few kind of things to talk about in general, but really this is going to be a look at some of the examples, right? And NASA has some super cool visualizations. Oh, crab sticks. This thing pisses me right off. Let's see if I can find it. No. That's a good one. Check that out. This is the view of a circumbinary star system, which is Kepler 16. Right, so Kepler is the space telescope that discovered Kepler 16b, and they think it has a moon. So if you are standing on its moon, this is what you'd see. Isn't that just amazing? So super cool. Come on, get off. All right. Anyway, so really most of the lecture is hopefully going to be spent checking out stuff like that, because that's just fun. And I keep getting little flashbacks of Interstellar while I'm doing this. I don't know how many of you have watched Interstellar? All of you, hopefully. Someone? Someone's. Paul, you've got to have watched Interstellar.
I've missed it, man. I got to admit.
What?
Love Chris Nolan, just never got around to it.
Shit, me, you're kidding me. Oh man, I'm sorry. I'd like to say that I still respect you, but I just don't know anymore. Anybody else? Has anybody seen Interstellar? Should make that. Oh, good. Someone's seen it. SV Gone. Who's SV Gone again? Go on, they've got to have a voice.
That's me.
Who's you?
There.
That doesn't bloody help, does it?
If it's not considered trash to Paul, he's not gonna watch it.
That's not true. Christopher Nolan
Hey,
movies are
yes, it
usually
is,
really
Paul.
good.
Is
I
that,
do like trash, but
is
that's not
SV
here nor
Gone
there.
Sam by any chance?
Yes.
Oh,
Yeah.
okay. I thought I recognized the voice. You just saying it's me. It's like saying someone say, "Where are you?" You go, "I'm here." Okay, well, there's that. Okay, all right. Well, so consider this like your homework for the week. This is like kind of adult school. Watch Interstellar. It will bend your mind in all kinds of funky ways, and I still can't figure a lot of it out. I actually tried explaining some of the. Oh, geez, I'm not too sure it was like the quantum relativity or whatever it was to my wife at about 1 o'clock in the morning once when we watched that film. That was, I think she was actually asleep. I'm not sure, but she sure was afterwards. But yeah, it's absolutely fabulous. And they have, obviously they're going to different planets, right? And some of them, I mean, it's all based on really good science. A couple of research papers came out of that film. Like the people who are, acting as science consultants, they actually ended up publishing some of their work. It's just so that's like the ultimate badge of like science geekdom for a sci-fi film is to actually have some of that, the stuff behind it published. Hang on, let's see if we can find up a real cool. Fucking it's this bloody bar at the top. Just go away. All right, let's see if I can sneak up there before it realizes I'm there. There we go. Oops. Check this out. So this is actually a visualization of a black hole, which is one of the planets that they're visiting orbits around, and this is an actual visualization of a black hole, like the first time we've been able to see one. Kind of can't really see one, but you can see the event horizon around it. And so it has this shape because it has such immense mass. It bends the view of that event horizon behind it round. We were talking about gravitational lensing the other class. Well, this is gravitational lensing on steroids. And so it's actually a disk, but you view it like that as well, because it actually bends that light around. So it looks like this. It is absolutely freaking cool. It is, I'd say one of the best sci-fi movies I've ever seen, and I've seen an awful lot. I've seen some really shitty ones too. Anyway, so yeah, it's really well worth watching. If I'm going to give you any advice on film watching, and some of it's, I think it's good. I have a pretty good taste in films, according to myself. Interstellar is fabulous. Anyway, I got all excited there. Just thinking about, I'm going to have to go watch it again today, probably. I think I think it'll be my 4th or 5th time. Anyway, so come on, love. Anyway, so just a few quick things before we get on to the really fun stuff. I don't think I mentioned the Spitzer Space Telescope. This is actually a really important telescope, still up there and about, because it can, so it's the generation after Hubble and before Kepler. What the hell was that? That was my cat, or one of them anyway. But it's very good at picking up infrared, and so this is actually the telescope that they use a lot to look at planets, exoplanets in the infrared. And it's also how, where'd it go? They've been able to partially map the clouds of Kepler 7b, right? This is a hot Jupiter. We'll get to that in a bit. It's about 1.5 times the diameter of Jupiter and about half its mass. Has a density of styrofoam. What is that cat doing? Oh, schizo creature. Another quick thing, just to I talked about Kepler having a very kind of focused view on our galaxy, and this is a real cool picture to show that. So that gives you an idea of what a tiny, tiny fraction of our galaxy Kepler has actually looked at, right? And so we're out here in one of the spiral arms, kind of out in the boonies, to be honest, you know, in the, I don't know, West Virginia of the Milky Way, essentially. And Kepler's looked at a very, very kind of focused look at a particular part of that arm, which also causes problems because a lot of the exoplanets it finds are around stars that are a long way away, which makes it hard to figure stuff out. Another quick look is at figuring out atmospheres, right? So this is only really something that you can do for star systems that are relatively close, like within, I think, probably a couple of 100 light years away, give or take. And this is very much the same as what we talked about way earlier in the course, particularly with the Galileo mission and its view of Earth. So you can either do a absorbance spectra, right? So that's essentially when you have your star and the planet passes in front of it, you can see which wavelengths suddenly go missing, right, from that that spectrum that's emitted by that star. Or if it's close enough, you can actually look at reflected light. That's what they've done for another star. Let's see. Oops, not that one. Not that one. Here we go. This one. So this is a picture of a solar system. It's got 4 planets in it. Don't know why they did it, numbered them inside out. But anyway, they're able to detect methane and carbon monoxide in its atmosphere of this one here. And so this is a view in the infrared from the Spitzer Space Telescope. It's going to start getting crowded up there with these space telescopes going up. James Webb is going up soon, and that's going to be very exciting. That's a big one. And also, just to confirm, the number's a bit out of date, but the proportions are more or less the same. Because of those biases that we saw in observation, right? So radial velocity, where you have the kind of the wobble of the star, right? The Doppler photometry, that is biased towards massive planets that orbit quite close, right? Because they're more likely to produce that radial shift and change in the light emission of or observed light emission of the star. And similarly, transit photometry, obviously if you have a small planet far, far away from the star, say, you know, someone like Pluto, right, which isn't actually a planet, sorry, Paul, then you're never going to detect that planet by transit photometry because the small tiny dip in the output of that star would just be lost in the noise, right? You need something much closer in that and much larger, right? And so that's why this Kepler, is it 7b? Yeah, was one of the earlier discoveries. I think it was actually part of the kind of tuning up of the Kepler Space Telescope. It was how they found it, and we'll see what that looks like in a second. Anyway, so yeah, the bias is typically towards larger, more massive planets. So ice and gas giants are kind of the top category, and then you've got super Earths beneath that. And super Earths are basically things that are smaller than Neptune but larger than Earth, typically around 2 to 5 times the mass of the Earth. So they're thought that they can be rocky, right, in part, but they're much larger than the Earth is, and we'll have a look at one of those in a little bit. Another thing to look at is, let's just move this over here. Save that first. Come on. Dum, dum, dum. This is kind of a basic plot of the various exoplanets that have been found and kind of their habitable zone of their stars, right? So if you have star mass on this axis, right, and ours is about here, G-class star, you're an M dwarf down here and an O-type, you know, super bright. I don't know if it's called O because it's like Orion, I don't know. But anyway, really bright, shorter lived star. You can see how the habitable zone gets closer in the smaller the mass and further out the larger the mass, basically because of heat. Right, the more massive the star, the hotter it is, and therefore the further out you have to go before you can find liquid water. And so if you look at the discovery, like these are bands basically between dry terrestrial planets, that would be something like Venus, maybe Mars, right? Earth-like, which implies liquid water, and then gas giant, right, which implies you know, something like Jupiter or Saturn, essentially. And then you actually look at where most planets have been found. Almost all of them, partly because of that bias, have been found, you know, way further inside the orbit of those potential habitable zones, right? And so it's kind of like, you know, you look at all these stars, most of them have planets, right? That's generally the rule, I think, by now, right? It's not the exception. But most of those planets are not orbiting, at least the ones we've detected, right? There may be others in those solar systems, but most of them are not in those potential habitable zones, right? So that's kind of, you know, you get all excited when you hear about how many thousands have been found, but then you start kind of paring that excitement back a little bit when you realize that, you know, a lot of them aren't really anywhere near where they need to be habitable, essentially, at least by our definition. I think one of our cats has gone into the catnip. All right. And so essentially a lot of the planets we found are called hot Jupiters. Cat cow. Oh, I don't know. She's just the weirdest cat. She really is. You might hear her yowling around in a little bit. She's knocking stuff off shelves upstairs for some reason. And so it's really interesting because before we started doing this whole exoplanet search, all of our knowledge about solar system formation came from our own solar system, right? And it's kind of, you know, the theory's neat. You know, you've got, you know, rocky terrestrial type planets closer in, you've got gas giants further out, you've got past the frost line, and you've got these ice giants further out still. So essentially, when the results started coming in, and it's like, well, no, we've got loads of Jupiters like close from the star, all that kind of got blown into the weeds. You know, so our understanding of how solar system forms is extraordinarily incomplete based on, you know, all the discoveries that we've found in terms of exoplanets. And we actually do think now that Saturn and Jupiter did migrate an awful lot further in, closer to the sun during the very early, you know, I don't know, billion years, let's say, of the solar system's formation. So there's all kinds of funky stuff that can be going. There's even things that they call rogue planets, a bit like Rogue One, but planets. And those are planets that are just wandering around. They don't have any star that they're orbiting. I don't know how that could occur. Presumably they got kicked out somehow. Something weird going on. Anyway, so that's just kind of catching up on some other bits and pieces that didn't have time for. Sorry, itchy foot. Last class. Now we get to look at the fun stuff. So, let's see if I can move this a bit further out of the way. Here we go. Obviously, this is all kind of reference to Star Wars, because that's such a, I don't know, culturally important story, I think, in terms of sci-fi. But let's see if this loads up. Come on. This is what Kepler 16b looks like. It's that purple dot that's zooming around. It's a planet around a circumbinary star system. I don't know if you can hear that. It's my cat yodeling. And so it has a G-class star. God, it just keeps moving. I can't point at it. A small, I think it's a K-class star, so it's not quite an M red dwarf. And then Kepler 16b is way out. Let's see what that looks like. And so there's this really cool holiday poster, right? Let's go out here. So this is just fun. This is what the Kepler 16 system looks like. How far away is this? Let's see. Did I put a note? No, I didn't make a note of how far away that is. You can, oh, here we go. 200 light years away from Earth. So fairly close in the grand scheme of things. It would only take 200 years to get there at the speed of light, or about 800 years, give or take, at our fastest. I actually think that humans can travel up to, at speeds of up to half the speed of light before they liquefy, which is kind of the, you know, us being soft, squishy things. I don't know if you put us in like cryogenic liquid suspension, if we'd be able to tolerate more, I don't know. But either way. And so this is what the Kepler 16b system looks like. Isn't that awesome? So 16b is actually within just the habitable zone, which is this zone here of this circumbinary star system. I don't actually know whether it would have a purely circular orbit based on the gravitational effects of two stars. I don't actually know that. I tried looking, I couldn't find it. And then if you look in closer, isn't this awesome? This is what they think Kepler 16b looks like. How cool is that? I spent ages playing with this. Let's see if, and the link to this is in the PowerPoint. Ooh. So it's pretty bloody big relative to the Earth. It's mostly gas, maybe some liquid on there. It's in the habitable zone, so it might be liquid water. What's it look like relative to Jupiter? Smaller than Jupiter. Anyway, there you go. Yeah. Oh, we're getting, everybody say hello to my neurotic cat, Caramel, one of my cats. Yeah, she's the one that's been running around yodeling. Can you hear it? Actually, that's... So Caramel has made her first appearance on YouTube education channels. Here you go. She's a pretty funny cat. I didn't get to see her tail all puffed up, which is even funnier. Let's stick this back here. So 16b is exciting, obviously, because it's a circumbinary system, and it's the first one of those that we actually discovered. And again, if you were to stand, or you can't stand on 16b, we don't think, because it's most likely a gas giant based on its size. But if they think that it has a moon, pardon me. So this is like a little bit like oh shoot, it's not is it Pandora? Sci-fi film with giant blue aliens.
From Avatar?
Avatar, that's it. Yeah, Pandora.
Yeah, Pandora's the planet.
No, it's actually not a planet, it's a moon. It's
Pandora is the thing that the movie takes place on.
Yes, that's right, and it's a moon. Sorry, sci-fi geek here. But anyway, this is kind of equivalent to Pandora. We don't know what the moon looks like. We don't know whether it has an atmosphere or not. But we're somewhat confident, based on the kind of slight wobble in the transit of Kepler-16b, that it has a moon. And so if you were to stand on its moon's surface, this is kind of what it would look like. Isn't that cool? I don't know, this is kind of part of the course where I kind of start geeking out. So hopefully you're not going to be too put off by that. So that's not a great candidate for like another Earth, essentially, right? Because it's a large gas giant. Maybe it's moon. This one's even weirder and wackier, and they've actually been able to look at 7b, its actual clouds. Let's see. No, that's 22b. Here you go. Here's 7b. So if you look at this now, right, this is a let's get background. It had this bright white spot on it, and they wondered if it was you know, produced because of heat, right? So that kind of appears white because of thermal radiation. And so they trained the Spitzer space telescope on it, and they figured out that it's not actually it's not sufficiently massive to produce that much heat. And as a result, so here you go, this is what it looks like compared to Jupiter in terms of size. They're pretty sure it is tidally locked to its, oops, gonna zoom in again because it's, you can see how far inside the habitable zone it is. And that's why it's so large, because it's so hot. It's basically, it's been expanded through the thermal input from its star. But it's tidally locked to its star. Orbits in, I think, 5 days. Right, so this is just doing like that around its star. But they actually think that it has a hot side and a cold side, so it has a terminator, which is kind of cool. So essentially on this hot side, it's so hot, I think it's around 1400 Fahrenheit, give or take. So really toasty. It's hot enough to actually have iron rain kind of falling at that terminator, where the basically kind of at this point here, right, where it goes from being in the sun to being out of the sun, that temperature is going to drop suddenly and cause precipitation, right, or rain essentially. Because it's so hot, they think it's actually a lot of metals. in that rain, which is, I think that's pretty crazy. So this also not a great place to be honest. Rather hot, not especially habitable. There's two other candidates I'm going to talk about today. Obviously, there are thousands and thousands and thousands of exoplanets, and so I don't have, or I'm not even sure we have as much information on all of those. Obviously, we focus on ones of particular interest and ones where it's possible to actually observe them. And so 22b is another possibility. So again, long way away. And this is what they think is a water world. So again, these are all hypothetical visualizations based on current data, right? And so what does that look like? I think that's a couple of times the size of yeah. So it's a kind of a super Earth, and it's thought to be largely an ocean world, right? So this is kind of what prompted me thinking about Interstellar, because one of the planets they visit is a ocean world with a, oh, I'm not going to tell you anymore because I don't want to spoil the story, but without any continents. Pretty sure it doesn't have a moon though, based on studies. So they think that this is largely an ocean world, partly because it's on the very inner edge. That's gonna, or even really just inside the habitable zone. So this is, it's not got kind of further out where that liquid water could start, you know, kind of solidifying, maybe kind of outside the habitable zone. It's not so far in that it's been evaporated by the star. So they think that it's mostly a water world. Does anybody have any questions? I'm just kind of rambling on and having fun playing with this stuff.
I have a question.
Who's that?
Kiara. Question
hey, Kiara.
extraordinaire. Hi. How is that possible? Like, is the water like just like, I don't get it. I don't get how the water can just stay in a circle and not just like go away. You know what I mean?
In terms of, well, the atmosphere is essentially what protects it from, or it's created by its evaporation, right? That's why we have liquid oceans and an atmosphere here, is in part due to, you know, the cycling of that water vapor. So is it the fact that it potentially doesn't have any continents?
Yeah, that's
flips your
the
mind?
big point.
Well, I mean, to be honest, where was it? Venus would have had, if it had, and we think it had an ocean very, very early on, before it kind of all evaporated through heat. But if Venus had an ocean, that almost all of Venus would have been underwater, because there's very little variation in surface topography. Right, it's kind of like if you go to, you know, Oklahoma or Kansas. You know, if you're standing on a motorway overpass, you're typically standing at the highest point in the state. So, and actually the Midwest was almost certainly an ocean or an inland sea. I mean, what do you do? Many, many moons ago, earlier on in the Earth's history. And essentially what happened is the Appalachians rose up, or the Appalachian orogeny, right, which is always a fun word, and essentially blocked that water. And so it just began, and also the uplift a little bit, and that water evaporated. And so that's one of the reasons why the Midwest is so fertile, and it's also so flat, because it actually is the bottom of an ocean. Yeah, here's another peck. There you go.
Hi, puppy. Also a big question. So there's more than likely like a rocky core, and then the water's on top.
Exactly. So it is almost certainly a rocky terrestrial-like planet. So if we go back here, right? So it's going to be one of those. It's a super Earth basically. So it's rocky, not a gas or an ice giant. So it's mostly silica and metal would be my guess. And they can figure that out for a lot of them, not all of those exoplanets, based on that radial velocity method, the Doppler shift. So even if they weren't discovered using that method, which they wouldn't have been if they're a Kepler object of interest, another telescope, particularly an earthbound one, can have a look at it. Oi! Stop it. Again, doing something she shouldn't on the couch. Can actually look at the Doppler shift and determine the mass. And so they're able to kind of figure out, based on orbital radius and that shift, how massive that planet is. And then they can compare that to the transit photometry data to get an idea of the size of the exoplanet. And so then they can work out density. And so that's how they figure out whether or not they're gas giants or if they're kind of rocky super Earths. If they have a density similar to Earth, then it almost certainly is because it's mostly a rocky metallic core. But they think in this case, and again, a lot of this is like, you know, inference and, you know, kind of looking at the data and basically drawing a picture, right? We haven't actually directly visualized Kepler 22b. We don't know what it looks like. So we just think that based on its position and its mass and so on, that it's a water world. We don't actually know for definite that it is. So always have to be a little bit cautious, because when they make these super cool visualizations, there's not an awful lot of data on which to base that visualization, right? It is almost an artist like conception of it, essentially. Did that help?
Yeah, that helped.
Yeah, but you definitely got to watch Interstellar.
How long is it?
It's a fairly long film. It's a pretty serious undertaking. I think it's about 2.5 hours.
Oh, that's not bad.
Yeah,
I'll just take like 30 breaks.
Yeah, that's right. You could watch it in 2 shifts. You could have your own intermission. I'm pretty sure it's on Netflix, I think.
It is not. I looked up earlier. It's on like Amazon Prime.
Oh, bugger. Well, anyway, hopefully you can find it somehow. It is super, super awesome. Oh, and they also do a very cool representation of time dilation, which is essentially if you're kind of trying to explain it. If you're traveling at a fraction of the speed of light, time passes more slowly for you than it does people observing you. Go on. And so if you were able to travel to, I think it's 452b. Which one's that one? No, that's 7b. Here you go. If you were able to travel to this one and observing it, an observer would observe you taking about 1400 years, but it would actually, in your own experience, take, I think, kind of 150 years or so. It's really, really kind of, and so they have a really cool representation of time dilation when they go down to visit that water planet, the person they leave behind, because time passes so much faster for them. It's like every minute they're down on the surface of that planet is something like an hour or a day or something crazy back up in the spaceship. There's a lot of really, really cool stuff in that film. So anyway, so
wait, can you drop a bootleg on Blackboard?
I don't think there'd be enough space on Blackboard, to be honest.
That sounds hilariously illegal.
Yeah, I might
Okay,
get in
but like,
trouble for
who's
that.
gonna catch us? Yeah,
Just download a VPN.
I don't know what that is.
Well, you're all smart adults. I'll leave it up to you to figure out. Anyway, so what we're really interested in terms of exoplanets are terrestrial, right? We need something that's within 5 Earth masses, and it needs to be in or very near to a habitable zone. And so one of the best candidates for that is 452b. Now, this actually sounds like, in many ways, like an Earth 2.0, right? It's a similar size to ours, has a really similar orbital period, similar orbital radius. Star is a G2 class star, just like our own, has a similar surface temperature, a bit older, a couple of billion years older, give or take, but it's like very, very similar. And if you look at its the 452 system, right? Star has a similar habitable zone to ours. The planet has a similar orbit to and place within that habitable zone to ours. It's a little bit hotter, so the habitable zone kind of extends out a little bit further, but really, really similar. So they think it's very rocky based on density, potentially volcanic. Unfortunately, it's too far away to visualize via the telescopes that we have, even the next generation ones, because it is, how far? 1,400 light years away. Holy shit balls. So if you was going as fast as the New Horizons spacecraft, it would take about 26 million years to get there. That's a really, really, really long time. So what does it look like? Let's have a look at the planet itself. Again, no, Robert, and well, certainly none of us are going to get there. And unless you can figure out how to travel faster than light without ending up like the crew of the Event Horizon, we're not going there, no. But there are some really cool ideas for getting to other places, and we'll talk about those next week. So anyway, in terms of, let's get this in a better plane. This is essentially what they think it looks like. I'm not sure why the NASA's habitable zone is a little bit smaller. Actually, I don't know. I don't know what the discrepancies are there. That's not a stupid question, Robertson. That's a question that has been occupying a lot of people for a long time. No way of knowing. Until we find some other form of intelligent life, we've got no way of knowing if we're the only ones or not. It is an unknowable answer, essentially. And I don't know. I mean, there's an equation, I forgot what it's called, which is basically if you have X number of stars and each one of those stars has a planet and so on and so on and so forth. Like, depending on what numbers you put in on that equation, you can figure out how many other civilizations there are likely to be. But it obviously depends on what numbers you put in to different parts of that equation. And you can look at it two ways, right? You can either look at it from the perspective of, we've studied a really tiny part of one galaxy, and we've found 4,500 planets, right, of which a reasonable chunk are inhabitable zones and look Earth-like-ish, right, like this one. And so if you extrapolate that over the whole of the Milky Way, right, that's one galaxy. And there are thousands of galaxies in the universe. Then the number of exoplanets is going to be in the millions. And so just by numbers alone, it seems likely that if life evolved here, then we're certainly evolved somewhere else. So the flip side to that question, or that outlook, let's say, is that if you think about the evolution of life on this planet and how many kind of near catastrophes there were, how many specific conditions there were in terms of, our magnetosphere protecting us from UV, but not completely, our atmosphere, the fact that somehow we've been bombarded by giant space rocks and we haven't all died, as life in general. The fact that those giant space rocks kind of shifted the trajectory of life on this planet in a variety of ways until we actually ended up as us, right? Because we're the very kind of end point of our planet's history, essentially. So if you look at it that way, every single event that happened that led to our evolution, or evolution of life which can make radio waves, let's say, every single one of those events could have had an alternative outcome, and there are a sufficient number of them that it's like rolling a dice, right? If you want to get 6 ones in a row, it's not a 6 plus a 6 plus a 6, it's a 6 times a 6 times a 6 times a 6, right? So that's why I don't gamble. It's a bit of a loser's game as far as I'm concerned. And I don't have enough money either. But the probability, the more of those events you have, the probability of, finding your way through and basically rolling, 6 sixes in a row, it gets smaller and smaller the further you go along. So you can take both perspectives, right? There's no real way of knowing which one's correct. It's very much an open-ended question. It's almost in a way a question of like, is there a God or not? Don't know, basically. And that's kind of, this, it's kind of where astrobiology starts getting into almost theology, right, in terms of the philosophical questions involved. So it's not a stupid question, one little bit. Anyway, unfortunately, there's not a whole lot more known about 452b because it's just so far away, right? It's very, very hard to visualize. All the information that we have is based off of its transit and its radial velocity. So we can't do atmospheric composition. We can't do direct visualization, can't do any infrared stuff like that because it's far, 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 far too far away to be able to get that resolution necessary. And that's the big downside of the Kepler mission, right? Because it's such a laser-like focus, an awful lot of the exoplanets it discovered are a very, very long way away. And so that's why TESS, the most recent space telescope up there, is surveying our near abroad, within 30 to 50 light years, in the hope that we'll get more candidates that are more amenable to direct observation. And James Webb will just accelerate that even further. And also the extremely large telescope array in Chile, I think, is where it's getting built. after the very large telescope array is just not quite enough. So anyway, there's that's kind of where we're at currently in terms of exoplanets. What I want to do on Wednesday, and I will update the study guide. That's kind of one of the things on my list of things to do today. What we'll do on Wednesday is look at two systems in more detail. One is the TRAPPIST-1 system, which is a 7-planet solar system, right, around an M-class red dwarf star. So super weird system, very much like the Galilean moons of Jupiter, actually. And also we'll be looking at Proxima b, right, which is the nearest exoplanet to Earth, about 4 light years away. And so that, Robertin, is within the realms of achievable sci-fi, right, in terms of at least getting a probe there. It would take a while, but there's a lot of really cool ideas about how to do that, including giant lasers and stuff, which is always fun. So yeah, that's pretty much what's on the cards for Wednesday. We've got a quiz on Friday, pure sci-fi on Monday, recap, and then the final exam is a week on Friday, and that's it. So there you go. I don't have anything more to talk about today. All these links are in the PowerPoint. I've added some stuff. I'll upload a new version in a second when I get off of here. But yeah, it's really cool stuff. If it's one of those things where, you know, it's always been the case that science is stranger than fiction, and I think science fiction is pretty cool because it allows people to kind of make like forecasts, essentially, or to apply what they think is likely to be found or what will happen in the near future, right? But use kind of sci-fi to explore those things. Like that's what a lot of really good sci-fi is about. And an awful lot of it's been coming true, which is just really cool as far as I'm concerned. And a lot of the stuff about exoplanets kind of falls into that. You know, there a lot of the different potential planets out there that we've kind of been, you know, imagining. You know, we're actually finding them, and so I think that's super fun. Anyway, so anybody have any questions? Anything that they want to get clarified or thereabouts? No. So Kiara asked, is the final comprehensive? The answer is no, it's not. It's just on all the stuff. Oh, there's another one of my cats. All the stuff since spring break, since the end of spring break. I'll write that down so it's in the record. However, obviously, as with all subjects, courses, and exams, you know, you should understand some of this stuff a lot better now and apply some of the things that you learned earlier on. Like we're talking a lot about habitable zones. And so really that's something that we talked about a lot earlier on in the course, and now it's clearly applicable, right? So even though, you know, I'm not going to be testing you on stuff in the first half of the course, a lot of the stuff that you learn in the first class, you should be able to apply that to what we're talking about now. Any other questions? No? All right. Well, thanks very much, everybody. I had a lot of fun. I hope you did too. And I'll post all this stuff up in the next hour or two is the plan. Okay. See you all on Wednesday.
Have a good day.
You too.